Hello and welcome to our next lecture on cryptography. Let's start with the brief outline for today's talk. We would start with DES, it's an acronym for Data Encryption Standards. Then we will look at a couple of more acronyms: IDEA, PGP, RSA and DH protocols. So, basically today we are going to go through a set of algorithms and protocols. So, let us start with a quick recap what we have studied so far. We have looked at introduction to cryptography, followed by symmetric key and asymmetric key cryptography, and we had a very brief introduction to cryptanalysis. Now, the basic premise is that we start with a plain text, go for encryption and obtain a ciphertext which is not discernible to the unintended users, but the intended valid user goes through a decryption process and gets the plain text back. We looked at the symmetric key encryption. We start with the plain text, again we go through the encryption block using one key and then we receive the ciphertext. The ciphertext undergoes a decryption using the same key and we get the plain text. So, this was the symmetric key or the secret key encryption method, because the key needs to be kept secret in order to preserve the authenticity of the message. Now, we looked at symmetric key algorithms which are of two types: block ciphers, where we process block by block and encrypt each block using a key or a set of keys or sub keys, whereas stream cipher works it is like the convolution encoder we have seen, it is with memory, and that the current output depends on the past inputs and current input. So, now we go on to look at some of the standards past, present and future which help us understand how we use the theory in practice. So, we looked at this data encryption standard from the classical perspective, because this is kind of now obsolete. It has been replaced by AES, the Advanced Encryption Standards, but for classical reasons let us look at it. So, basically it was created by IBM in the 70s, and what it did provide and it still does provide is a very high level of security with limited key size. So, remember, the security depends on the key and not on the secrecy of the algorithm. So, DES algorithm is out in the open, right. So, this is a very efficient algorithm, classically important, and it is most importantly the stepping stone for the next generation encryption standards. So, the next generation is the Advanced Encryption Standard AES, which is now used worldwide, and it supersedes the DES or the Data Encryption Standard. With that background, let us quickly look at what DES does and how does it work. So, it is a symmetric block cipher algorithm. We have studied what are block cipher algorithms. So, the key length typically is 64 bits and it works with a block size of 64 bits. So, we take a non-coded plain text of 64 bit block and then work with it using a 64 bit. Being symmetric, the same key that is used for encryption and is used for decryption, and same is the setting for AES, but today we will just discuss DES in detail. So, what are the steps? The first step is a transposition which is carried out according to the set of a table, which is the initial permutation. So, the 64 bit plain text block is first split into two 32 bit blocks, and then 16 identical operations called rounds are carried out on each halves. Okay. This is made public, people know how to do this, right. And then the two halves of 32 bit blocks are joined back together. The 64 bit key is first reduced to 56 bits key by removing every 8th bit, and these are probably later used for error checking. So, 16 different 48 bit sub keys are then created, one for each round. So, we talked about those earlier 16 rounds. So, this is achieved by splitting the 56 bit key into two halves and then circularly shifting them left by 1 or 2 bits. So, these are the details. Basically what it tells us is that we subdivide the block and then we take the keys and then we do the permutations and then finally we carry out the encoding. So, different groups of key bits are used as different sub keys. The process that we just now discussed is called compression permutation due to the transposition of the bits and the reduction of the overall size. We call it as a compression permutation. After the key transformation, whichever half block is being operated upon undergoes an expansion permutation now after the compression operation. So, the details are as follows as how you can basically in this operation the expansion and transpositions are achieved simultaneously by allowing the fourth and the first bit in each block to appear twice in the output. Therefore, we replicate and therefore, we expand. We can look at it in terms of a diagram. So, you have this 4 bits and this fourth bit is replicated. Similarly, this fifth bit is replicated. So, we kind of expand. So, this is the expansion permutation. This is a spelling mistake here. But what does this buy us? This expansion permutation achieves 3 things. Firstly, it increases the size from 32 bits to 48 bits. It produces a longer string of data for the substitution operation that subsequently compresses it. And most importantly, because of the subsequent substitutions, the first and the fourth bits appear in 2 S boxes, which we will describe shortly. S boxes stand for substitution boxes, and the effect of this is that the dependency of the output bits on the input bits increases rapidly, and so therefore, does the security of the algorithm. So, after this in DES, the next operation is substitutions on the expanded blocks. There are 8 substitution boxes called X boxes. The first X box operates on the first 6 bits of the 48 bit expanded block. Similarly, the second S box on the next 6 and so on and so forth. So, again these are the details, these are openly available, and the net result of the substitution phase is that 8 4 bit blocks that are then combined into 32 bit block. So, basically we break it up, do the operations, do the permutations, do the expansion, then combine them back into 32 bit block. These are the details of the operations. So, this is how this 8 S boxes work with. So, you start with 48 bits, then divide it into S boxes and then go on to get the 32 bit output. So, the 32 bit output of the substitution phase then undergoes a straightforward transposition and using a table sometimes known as the P box for permutation box, and basically after all the rounds that have been completed, the 2 half blocks, remember we started off with 2 32 bit halves, are recombined to form the 64 bit output. The final permutation is performed on it and the resulting 64 bit block is finally the DES encrypted ciphertext. Okay. So, just a series of steps can be encoded into a computer program very easily. The decryption part is quite easy, provided you have the right key. Thanks to its design, the decryption algorithm is identical, but in the reverse order of the encryption algorithm. So, whatever we do splitting, we do combining, we do substitution, we can undo that in the decryption process. The only alteration that is made is to decrypt DES ciphertext, the subsets of the key used in each rounds are used in the reverse order. DES is really no longer used. Today we use AES, but you have understood the concept. AES is based on the Rindel cipher developed by 2 Belgian cryptographers, Joan Damon and Vincent Riemann. And this Rindel cipher that we use in AES is it belongs to a family of ciphers with different keys and block sizes. So, this in general gives a bird's eye view, so to say, of the DES, how it does and how you can go and make the different steps in order. We now move on to the next so to say de facto standard, which is called the International Data Encryption Algorithm, or the acronym is IDEA. What does it do? Well, it was created in 1990s and it was originally called the Proposed Encryption Standard, even after it was proposed. And then in the following year it was strengthened and it was called the Improved Proposed Encryption Standards, or IPES. Later on, the next year, the name was formally changed to International Data Encryption Algorithm, IDEA. Okay, and that is how it is known, and we know IDEA as being used in PGP, or the pretty good privacy, which is pretty common for securing our emails. We will spend one slide on PGP later on in this talk. Well, the good news is in 2012 the patents regarding IDEA expired and now it is patent free and thus free to use. So, we can expect a lot of proliferation for this IDEA. So, let us quickly spend a few minutes on looking at overall how IDEA works. First of all, IDEA is a symmetric block cipher with a key length of 128 bits. So, immediately the strength of the algorithm goes up because the key length is pretty good. So, block size used is 64 bits, and as with DES the same algorithm provides the encryption and decryption. So, it is symmetric. IDEA again has some rounds, actually 8 rounds using 52 subkeys. Rest is a matter of detail how these rounds are executed and how these subkeys are formed. Each round uses 6 subkeys with the remaining 4 being used for the output. So, firstly what do we do with this 128 bit key? It is divided into 8 16-bit keys to provide the first 8 subkeys. The bits of the original key are then shifted 25 bits to the left and then it is again split into 8 subkeys. These details can be worked out, and the shifting and then splitting is repeated until all 52 subkeys have been created. So, what do we do with them? The 64-bit plain text block that we have to encode is first split into 4 blocks. So, remember the key length was 128, which was used to generate subkeys, but the block length for the uncoded, the plain text, is 64 bits. We first divided it into 4 16-bit blocks B1 through B4, and then we have to do these keys, somehow operate the keys on the blocks to get the output block. So, for example, the output block 1 takes the first sub block of the plain text and multiplies XORed rather with the first key. Similarly, second one is with the second key. So, you have these operations that you can carry out up to this 14 output blocks. Again, very easy to implement in hardware. Okay? These are all multiplications. So, now what do we do in the input to the next round? We complete the first round. The 4 sub blocks are used in that order: OB11, OB13, OB12 and OB14, and after the 8th round 4 final output blocks F1 through F4 are used for the final transformation to produce the 4 sub blocks of the ciphertext. And how are they formed? Again, C1 is F1 star SK49 and so on and so forth, and you get the ciphertext eventually C1, C2, C3 and C4. These are the ciphertext blocks. Now, let us look at the advantages. First of all, it is the speed, very good for real time operations. We are comparing it with DES for classical reasons, but the point remains the same. DES is almost twice as fast as, so IDEA is twice as fast as DES, but at the same time more secure. So, brute force approach would require you to try all 2 raised to the power 128 possible keys, which is huge. I mean, if you look at 1 billion key attempts per second, it will take you 10 raised to the power 13 years, which is more than the age of the universe. So, it is pretty secure. Let us spend a couple of more minutes on the next family of ciphers called the RC ciphers. They were designed by Ron Rivest for the RSA data security. They are also called Ron's code or Rivas ciphers, that is the RC acronym. So, there is RC1, RC2, RC3, RC4, so on and so forth. RC2 was designed as a quick fix replacement for DES, that is more secure, more efficient. It is a block cipher with a variable key size and has a proprietary algorithm. So, in a way it is the disadvantage. RC2 is a variable key length cipher, and so it is used also in the Microsoft based cryptographic provider. The key length is 40 bits hardwired, and when using this Microsoft enhanced cryptographic provider, the key length could be put to 128 bits by default, right. Similarly, we have another example of RC4. It has a variable key size, but this is now a stream cipher as opposed to the block cipher. So, we do not really know the details of the algorithm, but it is very easy to describe and program, and just like RC2, it is also supported by Microsoft based cryptographic provider. The next version RC5 is a block cipher, again designed for speed. So, basically there is a trade off between speed and security and the key length. Of course, the computational complexity also comes out. So, RC5 has a variable block size, key size, number of iterations, all of them can be fixed by the user. What is very interesting is that the key size, which has a direct implication on the security, can be as large as 2048 bits. So far we have studied this private key encryptions, symmetric key, where the same key is used for encoding and decoding. We now change gears and we look at the public key encryption, where we have the notion of a public key and a private key. We talked about it briefly in the previous lecture, but let us look at some examples and consider it in more detail. So, public key and algorithms by definition are asymmetric. So, the key used to encrypt is definitely different from the key used to decrypt. So, the encryption key is called the public key, whereas the decryption is called the private key. This type of algorithm has a number of advantages, right, because the key transfer, key exchange, it is really much more efficient in this case. Okay. So, the basic idea is that the recipient can make his or her public key available widely, and anybody who wants to send the message can use the public key to encode and send, whereas it can only be opened by the private key. So, only the recipient, intended recipient, the legitimate receiver with the private key can decrypt the message. So, the disadvantage of public key algorithms is that they are more computationally intensive. So, it is okay for short messages for key exchange, but not for large volumes of messages. So, public key cryptography standards, the PKCS, are specifications produced by the RSA labs in cooperation with secure system developers worldwide. So, let us now talk about one specific example called the RSA algorithm, named after Rivest, Shamir and Adleman, the three inventors, right. It is the first effective public key algorithms, and it has stood the test of time. So, public key algorithms, as we know, rely on being computationally infeasible to recover the private key from the public key. That is the basic premise. It is the computational difficulty which prevents the hacker deciphering the message. So, what does RSA rely on? The basic idea is that it believes that it is easy to multiply two large prime numbers, but extremely hard to factor them back. The one line motivation regarding RSA: easy to multiply, difficult to factor. Factoring a number means finding its prime factors. So, for example, here we know 10 can be written as 2 into 5, 60 again can be broken up, and these are obvious, but the moment I go to slightly larger number like 2 raised to the power 113 minus 1, factorization becomes extremely hard. So, in this example you can see going from multiplication, going from the right hand side to the left hand side is very easy. I can multiply them and get you this big number, but given this huge number, getting the factors is a hard task. In fact, some of the good efficient computers are tested for this speed by giving them difficult numbers, large numbers to be factorized and to check whether they are prime numbers. So, how do we make this RSA algorithm work? The algorithm is as follows: two very large prime numbers. Large? How large? Are there enough large prime numbers? We will ask those questions, but let us assume that there are enough large prime numbers. So, we pick two of them. Two very large prime numbers, normally of similar lengths, are randomly chosen and then multiplied together. So, a and b are multiplied to get n, and then we get another number t as a product of a minus 1 times b minus 1. So, a third number is also chosen randomly as the public key e. So, it is chosen such that it has no common factor. What does it mean? That it is relatively prime with t. So, it has no common factors with t. And how did we get t? A minus 1 into b minus 1. What is a? One of the prime numbers picked at random. B is the other prime number picked at random. A and b are of similar sizes. So, how do we get the private key? Because the public key was chosen randomly. So, to get the private key, we compute d as E inverse mod t, and to encrypt a plain text m, we take m raised per e mod n. So, please note, what are we doing? M into m into m, so and so forth, e times. Therefore, we get m raised per e. But remember, we are working with large numbers. So, e can be really large. So, self multiplication many number of times could be difficult, and then of course, we have modulo n. How do we decrypt? Well, to decrypt, getting back the message m from the ciphertext C, we take C and then multiply with itself d times. But what is d? D is the private key, and this is also very large. So, again you can see computationally it is really involved. Let us take a very simple example. This is a toy example because the prime numbers will never be so small, they will run across the slide. So, let us take prime number a as 37, prime number b as 23. So, we get n as a product of these two prime numbers. Similar, t is a minus 1 into b minus 1, and we multiply and we get this number. Now, we must choose the public key e. The condition is that the public key must have no factors other than 1 common with this t. So, again a very small number 5, we find out that 5 is not a factor of 792, and easily we can pick e as a valid public key 5. So, to generate d, which is the private key, we take 5 inverse mod 792 and you get this number, all right. So, once you calculate d, you can now go for getting a ciphertext. So, suppose we want to encrypt G, a letter G. So, we first letter G, if you see it is the 7th letter in the alphabet. So, we say that okay, I encode 7. So, G represented as 7 becomes my message M, and the ciphertext is obtained as m raised to power e 7 raised to power 5 modulo 851, and that gives us 638, just computation, and decryption is again m is equal to c raised to power d modulo n, and we decrypt using this and we get back 7. So, even with this moderate, these small numbers, we have this kind of a 638 raised to power 317 modulo 851. So, again you can see that the computation is pretty involved. So, what does RSA algorithm rely on? relies on large prime numbers, but question again is, look, if everybody in the world has to use RS algorithm, do we have arbitrarily sized prime numbers to begin with, and do we have enough of them, or are we going to repeat these keys? We do not want to, we should have as many keys as possible. So, we would like to answer this question about do we have enough large prime numbers. We talk about this prime counting function. The prime counting function pi as a function of n just counts the number of primes that are less than or equal to n. Okay, that is the prime counting function. Let us say n. So, if you look at this prime counting function, you have prime number, yes. So, increment it by 1 pi n, 3 prime number, yes, 2, 4. So, n is 4, but this is no longer a prime number. So, the count remains 2, and then 5 prime number, count increases, 6 prime number, no, count does not increase, encounter another prime number. So, pi as a function of n increases, and so on and so forth. This is a prime counting function. So, this function is monotonically increasing, and with that. So, if you look at the question of are there enough prime numbers, well, let us see whether they are enough or is this infinitely large set. So, let us assume that we only have finite number of prime numbers, and let this set be p 1, p 2 up to p n. So, we have in this world only n prime numbers, that is the assumption. Let us see whether this assumption is right or wrong. So, let us make another composite number m as a product of these prime numbers plus 1. So, m is larger than any of the prime numbers, and so since there are only so many prime numbers, right, m is larger than this, and m is a composite number. But if it is composite number, it should be divisible by some prime number, because that has to have a factor. It is a composite number, it is not a prime number. But if you divide by any one of them, na, because these are the all known prime numbers we have assumed, you always get the residue as 1, the remainder is 1, because it is product of all these prime numbers plus 1, which means that it is not a composite number. So, there is a contradiction, and therefore, we have infinitely many prime numbers, and that is a saving grace, because RSA requires us to have infinite supply of prime numbers. What is the security of RSA? Well, the security of RSA algorithm depends on the ability of the hacker to factorize numbers, because we have assumed it is easy to multiply, difficult to factorize. So, we know that better methods of factorization are coming out. The current best is the number field sieve, and of course, on top of that we are getting very fast computers which do this factorization much faster. So, it is just a race. With quantum computing coming in, RSA is at a bigger threat. So, as the theory and computer become more efficient, larger and larger keys will have to be used. We go to now the next, so to say, de facto standard, the pretty good privacy. PGP is a hybrid crypto system, right, created in 1991. It was released over the internet by Phil Zimmermann as a freeware program, and it was intended to be used for email security, but it can be used for a variety of applications. PGP provides cryptographic privacy and authentication. So, both of them are there, which is very important for email security. I would like to know who sent me that email, whether it is reliable. And its next avatar, OpenPGP encryption, can ensure secure delivery of files and messages, as well as provide verifications of who created or sent the message using digital signatures. PGP and its source code is freely available on the internet, and this means that it has been subjected to an enormous number of tests, enormous amount of scrutiny by cryptanalysts, and therefore, it should instill a lot of confidence in the users. Let us look at another interesting cryptographic method called the elliptic curve cryptography, or also called as cryptography on the elliptic curve, ECC. So, let us see, most public key crypto systems get their security from the assumed difficulty of inverting a one-way function. You can multiply two numbers, but not factorize, and so on and so forth. ECC has become important mainly because groups have been found in which sub-exponential algorithms to invert the discrete exponential functions are not known to exist. We will talk about this jargon in a short while. What do we mean by this discrete logarithmic problem and discrete exponentiation functions? So, thus one has to use the standard exponential time algorithms to break the security of the conventional public key crypto systems. The basic advantage of ECC or the elliptic curve cryptography is that they are equally secure with smaller key sizes than their counterparts like the RS. So, smaller key size, but equal security. So, it is kind of an example to understand. Let z sub p be the set of integers 0, 1, 2 up to p minus 1, where p is an odd prime number. Okay. Let us define an elliptic curve over z p as follows. So, we are going to define using an example of an elliptic curve y squared equal to x cubed plus a x plus b taken modulo p. This is my elliptic curve, and all my calculations, multiplications, additions will be done over this curve. We will tell you how. But what are a and b? A and b also are elements of z of p, and we put a constraint, since there is an example 4 a cube plus 27 b squared is not equal to 0 modulo p. So, this is my definition that we are going to use for the elliptic curve in this example. So, for any a and b in Z p, the above equation has a pair of solution x comma y, remember. So, we have this x and y here, which is defining. So, x comma y is a point on this curve. So, we are now going to talk about points on this curve defined by this y squared is equal to x cubed plus a x plus b with some constraints. So, E Z p is the tuple x comma y such that x comma y lie on the Z p, and x and y are such that this condition is satisfied, y squared is equal to x cubed plus a x plus b modulo p. And what are a and b? Again we have put this constraint. So, the resulting set E as a function of Z p consists of all pairs x comma y element of z squared p. So, basically we have found a set of points, and all we are going to do is work with this set of points. In addition to these points lying on the elliptic curve, we also consider a point 0 or O at infinity. So, it is together they form the complete set of points on the elliptic curve. What are some of the properties? Well, any point p plus O is O plus p for all points on p, right, and if a point p given by x comma y lies on the elliptic curve, then x comma y plus x comma minus y is O, and this x comma minus y is also called minus p, because p minus p, where p is a point on the elliptic curve, should be O. And what is interesting is, if p lies on the elliptic curve, then minus p will always be a point on the elliptic curve. You can look at the symmetry. So, if p is x1 comma y1, this is kind of a toy example which will bring home the point regarding elliptic curve cryptography. So, let p be x1 comma y1 and q another point is x2 comma y2, right. Then clearly, if with p not equal to p q, we have p plus q as a third point. So, if you add 2 points on the curve, you get a third point also on the curve. And how do you get this addition? Well, there are 2 points coordinates x 3 and y 3. X 3 is lambda squared minus x 1 minus x 2 and y 3 is equal to lambda x 1 minus x 3 minus x 1. What is lambda? Lambda is given by this one, provided if p is equal to q and p is not equal to q. So, together we have a rule for finding out addition of 2 points on the curve, on the elliptic curve, and sum of 2 points is always on the elliptic curve. Now, where does this lead to? Well, I can always add p to it, p itself. So, I can get p plus p as 2p, p plus p plus p 3p, and so on and so forth to kp. So, self addition or multiplication is very efficient. So, elliptic curve cryptography relies on the difficulty of finding k given q is equal to kp. So, this is the basic dogma, that is what we are going to do. So, this property will be used in the Diffie-Hellman key exchange protocol based on elliptic curve, which we are going to look at the last example in today's lecture. So, it has the utility is already known of this wonderful mathematical technique. Let us look at a little bit more into this elliptic curve cryptography by considering a simple example. We put in numbers this time. So, let us say a is equal to 1, b is equal to 1. So, we have this elliptic curve y squared is equal to x cubed plus x plus 1, okay. And you can verify that 4 a cubed plus 27 b squared is not equal to 0 modulo p. What is p? P in this case is 23. Remember, we had this z which had 0, 1, 2, 3 up to a odd prime number p. So, what are the valid points? You can calculate, you can plug in, do trial and error, and you can find the set of all tuples valid points on this curve, and they are listed below. So, 0 1 you can substitute and you will find it satisfies the equation, and so 0 22 and so on and so forth. So, all the valid points, as you can see, this is the result of a computer search. I start with 0 0, then 1 1, then 3, I keep increasing and find the points on this curve. So, that is all. You take any 2 points at random, add them up, and you will get, it is a closed set, you will get a point on the curve. Okay, so, these are all the points listed out. We pick at random p is equal to 3 comma 10, here it is, and take q is equal to 9 comma 7. So, here it is. So, I took 2 points p and q on the set, and we are interested in finding out p plus q. So, we had those equations given earlier. So, we found that p is not equal to q, we use that lambda, and then we calculate x 3 and y 3 and calculate mod p. P is 23 here, I get 17 comma 20. So, I look in, and yes, lo and behold, I find 17 comma 20 as a valid point on the curve. So, this is the mathematics over the elliptic curve. So, this p plus q 17 comma 20 is also a point on this curve. And if you want to do p plus p in a attempt to find out 2 times p, you can calculate the subsequent lambda, and then you can find out x 3 and y 3 as 7 comma 12, and if you go back into this 7 comma 12 is also available. So, if you add 3 comma 10 with itself, you get 7 comma 12. And so on and so forth. I can find out 2 times p, 3 p, and so on and so forth, and this 2 p also belongs to the set. So, the elliptic curve is a discrete logarithmic problem to be considered. So, if you have this elliptic curve that we looked at with p is equal to 23, is equal to 9 and b is equal to 17. So, if change the a and b from 1 and 1 to this one, then you have a parallel problem here. And to give you the feel of this discrete logarithmic problem, we try to answer the following question: what is the discrete log k of q equal to 4 comma 5 to the base p 16 comma 5? That is, how many times should this p, right, p is a number 16 comma 5, it is a point on the curve. How many times should p be added to itself to obtain q, like p plus p plus p. So, k times p is q. How many times? K. But remember, there is a mod in place, and that creates the problem. So, the brute force method would be to try first 2p, check whether it is the same as q, no, then try 3p, check whether it is equal to q, not equal, until k times p, whichever matches q. Okay. So, I can try this effort p, 2p, but remember, calculating p and then 2p and then 3p requires some mathematics, or geometrically you can do on the curve, that is an easier part. So, in this example k is 9, this is the discrete logarithmic problem. So, bottom line, in the real world k is very large, and finding k could be computationally very expensive. This is exactly what ECC relies on. The elliptic curve cryptography relies on the difficulty of finding k given q is equal to kp. That is the basic idea. Now, last few slides we look at a practical application of this ECC in the form of the Diffie-Hellman key exchange protocol, which allows two users to exchange a secret key over an insecure medium. So, it is a key exchange or a key agreement protocol. Okay. So, it has two system parameters p and g. P is a prime number and g is called a generator, and we have this n equal to g raised to the power k mod p. We will look at a very simple example to illustrate the point. So, what does this DH protocol do? We have those two characters in the play, Alice and Bob, who want to exchange the key. So, Alice generates a random private value a and Bob generates a random private value b. They are both drawn from the set of integers. Then they derive the public value using p and g, right. And how do we do that? Well, the steps are as follows. Alice and Bob mutually agree on a number p. Okay. Alice chooses a private key k a known only to Alice, therefore, k sub a, and then computes k a p. Remember, there is the same time as a point p multiplied with itself. So, k a p using the elliptic curve, and this publishes k a p, right. But finding k is not easy, that is the computational difficulty that we have established. Similarly, Bob does the same job. He finds chooses at random k b, which is known only to Bob, and then computes k b p using the elliptic curve, same elliptic curve, and then publishes this k b p. Again, getting k b from k b p is difficult. Now, what does Alice do? Well, k b p is known, takes the elliptic curve and again does k a times k b p, but k is known to Alice. What does Bob do? Bob knows k a p, it has got its own k b known to Bob, it does k b times k a p. But lo and behold, we have k a times k b into p is same as k b into k into p, and magically they have these two numbers k a times k b into p, which are same. So, Alice knows this number, Bob knows this number, but the eavesdropper does not know the number. So, Alice and Bob have now secretly been able to exchange a key without the eavesdropper knowing it. You can graphically represent this. So, Alice chooses k a, calculates k a p, publishes it. Publish means puts it into the public domain. Bob secretly chooses k b, calculates k b p. Now, what is this p? P is known together, both of them, and known to the outside world as well. So, Bob publishes k b p, and then once they exchange it, then Alice calculates k a times k b p, Bob calculates k b times k a p, and then they decide to use k and k b as a common key. So, thus they have been able to exchange the key. So, with that we come to the end of today's lecture. We have looked at several acronyms. We started off with DES, which is the precursor of AES. Then we looked at the IDEA algorithm. Then we looked at PGP, pretty good privacy, followed by the public key methods RSA, and then we looked at the DH, Diffie-Hellman key exchange protocol. With that, we come to the end of today's lecture.